So I want to start off. We're going to talk about some networking, TCP/IP over the coming days, and I also want to talk about serial interfacing. And one of the things that you've done um, or doing in this week's lab is connecting up serially the uh, Node MCU, put in the AT with the AT firmware, and then we're using the other Heltec board, the ESP32, as our USB to serial interface. So the two modules are talking serial to each other, okay, so through that serial connection. And we have different serial protocols. You can have synchronous serial protocols, which has a clock and a data going by, and we have SPI, serial peripheral interface, or I squared C, inter IC communications. Difference between those is I squared C, you don't have a separate chip select. And so there is an address that is sent along, and then all the I squared C devices look at the address and say, is that for me? And if so, then they decode information. With SPI, what you have is a chip enable. And so there's, am I selected? Then the data is for me. So their address isn't encoded in that. Then we have UARTs. And so universal asynchronous receiver transmitter communications. And that's typically what you would used to find as DB 25 pin connectors, male on the back of a computer, or you might see 9-pin more commonly in the later years, 9-pin. There are still, I don't know if there's any, those have been fading away, and you see USB now. But you'll find them in routers, in all sorts of embedded communications gear. Serial is an important thing. Now, when you talk about serial on a PC, you are talking about specifically RS-232, which is the name of a standard that has been around since kind of the beginning of computers and before. And in fact, some of the first um, if you go and look at the voltage levels required, essentially coming out of your PC, if you have a serial connection, the data is coming out at plus and minus 12 volts. And the reason for that is way back when all the hackers, home builders and things, and there weren't PCs in the stores, you couldn't get printers. And so the only thing you could get was maybe some old telegraph office was getting rid of their teletype machine, and you could get your hands on an old teletype machine, and that interfaced at plus and minus 12 volts. In fact, RS-232, which is going to be plus 5 to plus 15, minus 5 to minus 15. And not only that, but your minus 5 to minus 15 is a 1. And your plus 5 to plus 15 is a 0. And that's what's coming out of your PC if you have a serial port. Okay, so you can't just plug in that to your ARM board or your Node MCU board, because that wants 0 to 3.3 volts kind of thing. The ARM board has a lot of I/O pins that are 5-volt tolerant, but certainly not more than that kind of thing. And so, and the reason that teletypes were, they were sending communications over a wire, and when you have minus 5 to minus 15 representing a 1, and plus 5 to plus 15 representing a 0, there's a good noise margin there of minus 5 to plus 5. There's a 10-volt swing that you can have noise on the lines, and you're still representing a 0 and a 1. So I remember years ago, a friend at school's dad had an IMSI 8080, and that's one of those first ones that had a panel of toggle switches, and you looked up the opcodes in a book, and then you found out what the ones and zeros to represent the opcodes, and you toggled all the switches, and you hit enter, and it incremented to the next address. And after about, I don't know, all night, 3 hours probably, of doing that, we were able to print out a little Snoopy and X's and O's on his teletype. It was the coolest thing ever. It was But we've come a long way from them. But we started out with serial because of the interface to the teletype. And then when printer manufacturers came along, they had to do that. And then they said, oh, the problem with serial is you send one bit at a time. Well, if we could send it in parallel, we could send 8 bits at a time, send a whole byte at a time, and all of a sudden you've got 8 times your throughput. So all printers went to parallel. So you had parallel ports. And so those were very common. And then one of the things about parallel is as you try to get the speed up sending data, they kind of act like transmission lines and they start interfering with each other. And that same kind of thing happened when you do hard drives. Hard drives, they had a limit in the speed, and then they all of a sudden got a bunch faster because they doubled the amount of wires and they put grounds between every other wire to reduce the crosstalk between the transmissions. And then as they were bumping into limitations, they went, let's just go high-speed serial again. And so they're back to serial, and all the SCSIs and SATAs and all of that are high-speed serial communications. So they were serial, went, oh, we need more speed. They went parallel, and then they started running into issues, and they went back to high-speed serial again. So that's where we are with our SATA drives, our USB, all of that is back to a high-speed kind of serial. That's a kind of long meandering road. You'll still find serial, and in fact, on a microcontroller, for instance, going and talking to different devices or interfacing to some measurement or test equipment, or like I say, the back of routers, oftentimes there's a serial interface. Now, again, if it's plugged into, if it's a computer or some kind of router, it's probably RS-232 serial, which is your plus and minus 12 volts. So you can't just plug a micro into it. You need some sort of interface. One of the things that we do now is we do like we did with your ESP32 is there's a little chip on board that will take USB on one side and convert it into serial on the other side. And that's what we're using in that mode to talk to the serial interface on our Node MCU. So our Node MCU, we used our USB to talk to the chip and program it, made it nice and handy. And then we are connecting to the transmit and receive on that board. So we're using that serial interface. And then on the ESP32, we are getting rid of the ESP32, essentially, we're holding it in reset, and then we are using just the USB to serial module. And you can buy those modules. There are different companies. FTDI is a big company, and I don't know, you might be doing stuff with Wayne with FTDI. We have modules in the back. Next term in the Linux course, you'll be using some of those modules and writing code for them and things like that to get output from an embedded Linux board or Raspberry Pi to go do things. FTDI was was the first company to really nail USB drivers in Windows. You would have all sorts of other companies, and their USB was terrible. And so Microchip, for instance, had a little utility buried in there with their programmers, and if something went wrong with Windows, this little utility would remove their driver and reinstall their driver because it just messed up. FTDIs didn't mess up. It was rock solid. They got to be a big company because of that module. And since then, support for USB has gotten a lot better across the board. You can get just standalone FTDI modules. Cypress is a common one. There's I can't remember the name. There's a couple of ones from China that don't come by default with drivers. Some of the Arduino boards use a 433 or something. And you can find the drivers out in the internet to make those kind of things work. So one of the things about serial is your transmission is at what's known as, if there's nothing going on, your line sits at what's known as a mark level, whatever that happens to be. So you're at a mark level. And then there is a start bit. And so you go down and there is this start bit. And so that notifies if I'm sending something on the serial, on the transmit line, I'm at this mark level, and then I drop down for a start bit, and then I send least significant bit first, the number of bits. So then let's say, I'm sending a 0, and then I'm going to send a 1, and then I send a 0, and then I send a 0, and then I send a 0. So let me see, start bit, and that was D0, 1, 2, 3, 4, 5, 6, 7. And so let's say I send something like that. And so there's my 8 bits, okay? And I could send, there's all sorts of options when you set up serial. Default is kind of 8 bits, but you can send 7 bits. And years ago, before everybody was just connected to the internet, you would contact bulletin boards. And bulletin boards, most of the time, were 8 data bits, 1 stop bit, no parity. That's typically, and by default, when we've gone and hooked up things, that's what you'll see, okay? But you can go and change that. And so if you had 1 stop bit, so then we will go to a stop bit, and so I'll say stop bit, and then it will just roll into the mark level, okay? But I could have, so this is 8 data bits, I could have 7 data bits even parity, which then would count up the number of zeros and decide whether or not there was an even number or odd number, and put the parity in there. Okay, and so here I've had a start bit, and then I've had a 0 and a 1 and a 0, 0, 0, 0, 0, 0, and then it goes stop it, and then it'll go into the mark level, told you to have another transmission. So the only other thing we have to really see with that kind of thing is how fast are you sending it? Now, what a UART does is, and you could bit bang one of these, and it used to be if you didn't have 2 serial ports or whatever, that you could just bit bang the transmission. Because if I send something out and I'm at a mark level and I drop down for a certain amount of time, and then in each time period, I either set it high or low, then I'm sending out serial data, okay? And so one of the things you have to look at is what is your bit time? And so if I go, for instance, here, and I say that's my bit time, for instance, if I'm 9600 baud, then I am saying 1 over that bit time, it's like 104 microseconds. Okay, and so 104 microseconds. So what I would do is you drop it down every 104 microseconds, you change the status of whatever the next bit is. When you are receiving it, what you do is you see that drop down and you go, okay, what baud rate am I? Let's say it's 9600, so 1 over, so it's 104 microseconds. You go 52 microseconds in and you look there. You look halfway. And then you look every 104 from that time. So you go to the middle and say, is it a high or a low? That's how you decode it. And you'll see someplace mentioned about the clocks, whenever you're at a certain baud rate, it's going to have a clock 16 times that frequency usually to try and get in the middle of wherever you are and look for it. And then say, and as long as I can be a little off here or there, as long as I'm not, if I try to shoot for the center, as long as by the time I get to the end, still within that 52 microseconds, I'm still going to read the right value. If the baud rate is off too much from what I set to what you get, I would start reading the wrong value. I'd get outside that bit time. So you can find it wander a little bit if I'm listening here, and then listening here, and then listening here, and then listening here, and listening here. As long as I didn't get on the other side of that and read the wrong bit, you're going to get the right data. So it's embedding the clock information with my kind of everything based off the start bit. And then I go, okay, go whatever the baud rate is, 16 times that, go to the center of that frequency and listen to it. So you could bit bang this. You could set and clear all of this. Now, on a digital side of things, we are going to be either This is either 5 volts or 3.3 volts, and down here I am 0. Now I said on RS-232, negative values are 1s and positive values are 0s, because that's what our teletypes were, okay? And so a mark level here, this is looking at the digital side of things. If I'm going to look at it on an RS-232 side of things, then I have +5 to +15, and I have -5 to -15, and my mark level is down here, and then I go like that, and then I'm over here, and let's say I'm there. Oops. And I've just kind of mirrored that, but at a different voltage, right? And so I'm where my mark level is here, it's at -5. So if I'm reading off the RS-232 port, when there's no transmission, I'm reading in the typically you'll see anywhere between like -5 to -15. Lab computers and stuff, typically 10 to 12 volts is something like that, or -10 to -12. One of the companies that made a fortune years ago with this kind of thing was Maxim. Maxim made a chip called a Max 232. And the Max 232 single chip, you could put -5 to -15 to +5 to +15 in one side, and it would give you the 0 to 5 volts on the other side. And you put 0 to 5 volts on one side, and it would do that. And it had little charge pumps inside with little capacitors, and it would all in one chip be able to do that, which was awesome. Because before that, if you bought a board from Motorola and you needed serial to go and communicate to things, you needed a positive and negative power supply to plug into your board, and that was difficult for people to come up with. So Max had this Max 232, one chip, a couple of capacitors, 4 capacitors, and you had to have a charge pump and be able to do the level shifting, okay, the conversions. That's the long and short of kind of serial. Now, I wanted to, let's see, you have a little device there in your kit, okay? That is coming from China. It's a little $10 or $12 device or something. It's a logic analyzer, okay? And so we can go and look at logic levels on the serial, on the TTL or digital side of things, not on the plus and minus 12 volt side. Don't plug it into your just directly without some sort of conversion. But I can have a look at the protocols. Now, I'll fire it up here. It uses an open source piece of software from a company called SIGROC. And if we go look at SIGROC, it's the project aimed to create portable cross-platform signal analysis software suite. And so it supports all sorts of boards, it supports all sorts of scopes, and so it's a nice kind of piece of software. And it's most of the back end is written in Python. Let's see, hardware support, let's go over to that and look at some logic analyzers, scopes, multimeters, LCR meters. There's a whole bunch of plugins for different boards that you can get. So all sorts of different things that are available here. So it's got a whole array of test equipment and things that you can go and connect with this, including some meters, all of that. So the software from there is called PulseView. And PulseView, now, sometimes it's a little tricky getting this thing up and running. And so if I go and look at, do I have it all? So it says no device. Let's go connected device. And the device we have is this FX2 LAFW unit. I'll see if it's, of course it won't. So this little board is emulating a Saley logic with 8-channel logic analyzer. So it's using this FXLAFW chip. I think it's a Cypress-based chip, and we'll just go there. And then it shows me I have D0 to D7. Now, one of the things with this is if you read the front of this this board, it shows you have channel 1 through channel 8. But we're in digital-based thing. We start counting at 0, and the software starts counting at 0. So your channel 0 is channel 1, right? So that's what you get. Okay. If I go and look at this, it says here's where I can configure the device. I can't remember what's in there. Oh, just frame limit and stuff. If I look at this, that says configure the different channels. And so if I go there, that shows me the 7 channels. It shows me whether it says, do you have analog? Do you have logic? All of this. Now, don't forget this interface. Different equipment can do different things. You could have analog channels. There are some units that have a couple of scope inputs and all of this. This is just a little 8-channel logic analyzer. It's like you having 8 logic probes, but better because it has memory. And so I hooked up on there it says channel 1 and channel 2. Here it's of course channel 0 and channel 1 and ground, okay, to my ARM board that's talking over to my board that is in the AT mode, okay, so talking to your device that is in that kind of mode. So I could, for instance, let's just see if we go and run this. See if it does stuff. Okay, and so it's running. It says it's taking 1 million samples at 20 kilohertz. So that may not be exactly what I want here. Let's have a look if I stop. So a couple of things. I've only hooked up channel 0 and channel 1, and it will give me all of that, but I'm going to just get rid of all the other channels so that we just see channel 0 and channel 1. Okay, and so that looks good. And I am sending data on the UART. I said that 104 microseconds, that was 1 over 9600. Okay, and there is you'll hear 9600 baud and 9600 bits per second. Baud and bits per second are not exactly the same thing. One of the things we have is a start bit, and we have a stop bit at least, and we might have a parity bit. You can have 1 stop bit, 1.5, or 2 stop bits. So the number of bits per second is not the number of characters that necessarily that you get sent at the same time. But a lot of times people just kind of use them interchangeably. The other thing is, as modems got more and more sophisticated, you could encode data so that more than 1 bit of information happened in a transition time. And so there's things like quadrature encoding and things that will give you more. Okay, 1 mega samples, and I'm going to say, hey, let's go up. If I'm 115,200 baud, which is a kind of nice figure to stick around. I think a lot of the Arduino stuff is 9600, which is exactly this, but I'm set for 115.2, and I'll just have a couple of million samples. We'll just do 2 million samples. Okay, and then so let's try and run it again and see what we get. See, I'm getting stuff. Can't remember what I programmed in there if I'm getting any. Yeah. Let me go over to, what do I got? Nice, not grabbing anything. Not sure why we're not getting anything. Okay, I'll have to have a look in a minute. If you look up here, this says add protocol decoder. If I go here and I go UART, and well, actually, let me just, before I do UARTs, let's have a look at all the different decoders. We have, for instance, 7-segment displays, RGB LEDs, the 7735 that you guys have for your TFT. IR, next term we'll use this with IR. So we have IR and we're doing NEC protocol. So it knows it. So you can see if you're actually getting data and what you're seeing with the data, because this will decode it. You just hook up the an IR LED, you hook up the receiver, you point your infrared remote at it, and this will go and grab the data and spew it out on the line, which gives it to you on whatever pins you have here, and then this will actually go and decode it. And so if I've got, in this case, we've got a UART, so let me go UART, then it brings up the decoder and you have to assign it channels. So you go to the decoder and you say, okay, what line is the receive on? And I'm going to say it's on D0, and this one I'm going to go on D1. And then what it'll do, I can say data format. Do you just want to see the hex values? Do you want to see decimal? It also says bit order. Now we're sending typically least significant bit first to most significant bit. But if something was sending something in another way, you can arrange that with the decoding protocol. So I said least significant bit first. I can display the decimal values, for instance, or just the hex values, or the ASCII values. If you're sending text-based stuff over the wire and you want to see if it's being transmitted or received, you can send it there. Okay, and so that should decode whatever we get. Now, if you don't see, and I have to have a look and see if maybe my lines are told or why I'm not exactly seeing a transmission going on here. But if you don't see this come up and you're able to grab the Saley logic device here, if this doesn't show up, then you need to play with the drivers that come with this. And when you go and install PulseView, it comes up with, it has a helper application to install drivers, and it's called Zadig. And so if I go there, there's Zadig, and it got installed with PulseView. Now you have to be careful with this thing. So right now it's showing me nothing here. And if I go options and I go list all devices, then this is showing me ST-Link because my ST-Link board is plugged in. And if I click down here, it's showing me FXLA2W, fingerprint, web camera, all the rest. it can show you um, for instance, if I have, if it's sitting on there, even if you don't go list all devices, it can just show you that. Don't install a driver because you're about to put the driver for your webcam and remove it with some other driver, which means your webcam no longer works. Okay, so you got to stop and think. Don't just click stuff if you install this thing. You need to find the something to do with the FX LAFW. Now it might show up as just an unidentified port. You might have to go into Device Manager and see which is it saying unidentified device, because maybe up here mine's showing FX LAFW, but it might say unidentified device. Okay, I definitely don't want it to be Bluetooth or my ST-Link or one of those. When you have that, there's different. It's saying okay, there whatever our driver is. I'm going to replace it with WinUSB 6.1, and there is a bunch of different drivers here, USB CDC, but it's the WinUSB 6.1, and I could go reinstall driver. I'm not going to right now, and that will make that work. Chances are it shows nothing in the driver window, and then there's an arrow and it says it will become WinUSB 2 if you install it, and that's what you want to do for this device. Make sure you're picking this device, because I've had people go and install this and then go, okay, now my mouse doesn't work, now all of this kind of thing. Now, one of the things, which one do I have? Oh yeah, let me just try unplug this guy. Gotta move him over there. My HDMI to USB and things doesn't exactly like everything. Let's put that there. And so that's, I think I messed that up. Oh yeah, not there. Let's see if that's okay. And so that's Zadig. Now, one of the things I found also with the new brand new computers we have in the labs is they don't like this at all on the front ports. Won't recognize it, won't see it. You need to be on the blue ports, the USB 3 ports that are on the back of the computer, if you're using the lab machines for it to pick this off. They haven't got a good, they've been asking the manufacturer what's going on with the front ports, because they are not 100% working with everything that we do. Okay, let me just go there. There, it probably would say. Let's just do a. Yep, still not sending stuff out for me. Awesome demo. See if in my code, my UART. Let's just go. Yeah, see the darn this HDMI connector is not the happiest thing. Yeah, yeah, not seeing it. Have to have a look at why. So anyway, that's should come up, should show you your transmission on the line, and not, like I say, you then go over, find a decoder, hopefully that you can get, and you assign it to the individual pins, and we should see some serial data. So I have to see what's going on with either this or that for not showing that kind of stuff up. Should be able to decode and show us serial data. Um, Again, you're going to see a mark level. We go down to a start bit, least significant bit, all the way, typically 8 data bits. The other thing that it will ask for is usually parity or no parity. And again, instead of having, no, it's usually designed, if we send ASCII, that's 7 bits, so your 8th bit can be a parity, and you can check on whether it's even or odd parity. Typically, it's sent no parity. Your choice is 1, 1.5, or 2 stop bits, and then it goes into a mark level for your transmission. And one of the things, if I'm not seeing stuff on the line, like I currently I'm not, I have to go back and look and say, it's not seeing any transmission. Why is it not seeing any transmission? Like, has the UART been enabled? Is it actually sending data out? And that's the kind of thing. So right here, I'm going, well, I was sending data out yesterday, but I'm not seeing anything on here. So why am I not seeing anything? The other thing is, when you go and do it, sometimes it's tricky to find out if I am, for instance, what's transmit and what's receive. And again, I was talking last day about data communications equipment, which is a modem, or data terminal equipment, which is a computer. And it's sometimes hard to tell, is the transmit pin actually talking about transmissions coming into it, which is a data communications equipment, or is it talking about transmitting data out? Here, we can say it's D0 and D1. Those are logic, those are like uh, different logic inputs. So we're scanning all the different channels, and I'm going to see data. So if my unit is outputting data, then I should see the transmission and then see the reception coming back from the other device. And then when I see this on the lines, then I can have my UART and say, okay, well, that's transmit, that's receive, and or change the pins around to match. Okay, so and then it'll tell me, am I seeing stuff from my ARM chip, or am I seeing it, coming back from the Node MCU or what have you? And if everything is right, then you should see that transmission going back and forth. Okay. Again, there's a lot of different decoders. Next term, we'll use this to have a look at our IR and decode the actual pulses coming in from the IR. And so that's all in there. But there's lots of stuff like I squared C. So you want SPI lines, and you're seeing if you're sending the right address to the I squared C device, because like I said, the address has to be sent in your transmission for the I squared C device to listen. Well, if you're not able to talk to an I squared C device, you can put this on and say, you think you're sending hex 16 to talk to an I squared C temperature sensor, but are you? And this will say, yes, you are. Sometimes I've had students, and they've had to bit bang out, so toggle things out on IO lines themselves, and they've shifted one too many or shifted one too few, and so they're not actually telling the receiving device the right address. This will tell you if what you're getting is actually what you thought you were getting. Okay. Um, so I'll leave it there. I'll have to go and see why what was transmitting yesterday is no longer transmitting. But obviously so I'm not expecting to get any data from my AT board because I'm not sending it out anything. So something has gone wrong in my code. Um, so I'll have a look at that. And then we are going to, not this lab, but in one of the coming labs, I'm going to have you fire up and have a look at your serial data going to this unit. Okay, so thanks. We'll leave it there.